The title is What Makes the World Go Round? And I know that sounds like a figurative title, but actually it's a literal title, and I really want to talk about what makes the earth turn. And you'll see it relates to water. And I issue a warning that the talk will be heretical. It will offer some suggestions and ideas that you might not have thought about. Okay, so it kind of all starts with this book, which I know some of you know about. And the essence of the book is about easy water and the splitting of water into negative and positive components. And the idea is that you have some kind of surface, a hydrophilic surface, and the water next to it. The water immediately adjacent to it turns negative, and that's easy water. And then you have positive charges here, and it's kind of like a battery. And that battery actually will be relevant in what I have to say about the Earth, because I think the relevance of this extends just beyond what we think of in ordinary aqueous solutions. And I also want to talk about the sun, and as you know, or as many of you know, the energy that's responsible for building this phase of water, in fact, comes from light, comes from the sun. And so that's critically important. And so essentially what I really want to talk about today is sun, is light, and charges. And I want to talk about the implications beyond just water. Okay, so first question is, maybe you never thought about this. We see day and night, and we see day and night because the Earth spins round and round with a 24-hour cycle. So I don't know how many of you thought about what makes the Earth spin. Okay, so we think, the general idea that we think of is that somehow, some years ago, maybe a few weeks ago, the Earth was given a spin, and it's got a lot of inertia, and it just keeps going round and round every 24 hours. And there's a reasonable idea, but after a while, you think that everything that spins like a frisbee or what have you suffers losses, energy losses, like, for example, the wind blowing and the tides and such. So this should run down, and if this is really true, you'd expect that the Earth would stop spinning on its axis after maybe 1,000 years, a million years, but it's been going for, as far as we know, like 5 billion years or more than that. I don't know the exact latest figure. And so the first question that I want to ask is, does the prevailing wind spin the Earth? Okay, that's an idea that I'm going to be entertaining. And then another thing you might never have thought of. So we're walking outside, and suddenly there's a gust of wind. And the question is, what causes the wind? Have you ever thought of that? What creates wind? You experience this every day, just as you experience gravitation. And we really don't understand gravitation. You're pulled to the Earth, you're sitting on your seat, and everybody knows that masses attract. But why do masses attract? See, so these are fundamental questions that are worthwhile thinking about. And so the second question that I'm going to deal with is, does the wind come from charge gradients? Okay, so the questions that I want to answer during this time are, the first one is, well, we think of charges as being trivial. There are a few static charges. You may get a shock if you happen to touch something in the winter and it's dry and it's windy. But how big are these forces? Trivial or more? And where do the charges on the Earth actually hang out? Do there really exist substantial charge gradients, or if there are charges, or they're just pretty uniform over the surface of the Earth? And can gradients actually drive the prevailing winds? There are prevailing winds. I'll be talking about them. And finally, can those prevailing winds actually spin the Earth? Okay, so that's the structure of what and the first question is, okay, well, how powerful are the charge forces? And I'm going to give you a few examples to demonstrate that charge forces are much more powerful than most of us think. Much more powerful. Okay? And the first is this. Okay, so if you put a proton next to an electron, and the distance, let's say, is distance d, so of course there's an attractive force, But there are two attractive forces, in fact. The first is the charge force, the electrostatic pulling force, and then also mass, because the proton and electron have mass, and when two things have mass, there's a gravitational attraction. So there are actually two forces, and the question that I have for you is which force is greater? And I think, I don't know what your response would be, but I think most people would estimate that probably the charge force is greater than the gravitational force. Would everybody agree with that? Okay, by how much? Okay, now I've got you because it's not so easy to answer. Well, the answer can be computed. It's not very complicated. A first-year physics student can easily perform the calculation, and the answer is by 10 to the 38th. So your question, of course, is, well, so how big is 10 to the 38th? It's a number that you don't really think about a whole lot, right? Because it's so far out of your realm. 10 to the 2, we understand, or 3, but 38. So this kind of illustrates where we're standing. So consider the diameter of a proton. Okay, it's pretty small. And if we're looking for something that's 10 to the 38th larger, how far do we have to go? So you think, okay, how about a tree? Now a tree has got a lot of protons in it, and it's got a big diameter. Is that no? That's not even close to 10 to the 38th bigger than the diameter of a proton. So you go to the size of the Earth, then you go to the solar system, and if you think that the solar system is maybe 10 to the 38th bigger than a proton, you're wrong. You're way off, because that's 10 to the 19th. So you got to get from 10 to the 19th to 10 to the 38th. So 19 and 38 are times 2, but it's not times 2 bigger. It's 10 to the 19th bigger. Well, it turns out that the right answer is that if you compare the diameter of a proton to the diameter of some kind of solar system that's far from any place that we are, you're talking about roughly the right ratio. The size of this cluster of stars to a proton is roughly 10 to the 38. And that's the difference between the charge force and the gravitational force. It's hugely different. Okay, here's another example. So you have two copper balls. And by the way, these examples are all taken from standard textbooks or what have you. You take two copper balls, and they sit on one another. And then you start removing electrons from this one and from this one. Now, these are pretty heavy. The question is, how many electrons would you have to remove from each one to get so that balls then become positive and they repel each other? And if they repel each other enough, this will rise up. So how many electrons do you need to remove? And the answer is 1 in 10 million. That's all. It's not really very many charges to remove to get these heavy copper balls to one of them to levitate. Okay, a third one is this. So you take an old-fashioned light bulb, let's say 120 watts. And the way the light bulb works is that you have electrons that flow through the filament, and as they flow through, they give off light and heat. So it's 120 watts, because the numbers come out right. And you collect all the electrons that flow through for 1 second. And then you take those electrons, and suppose you could put them here, and do the same thing with a second light bulb. Collect all the electrons that flow through for 1 second, put them here, put them 1 meter apart. The mathematics work out easily with one meter. And the question is, this, of course, will go in this direction. Whoops. Sorry. Will go in this direction. And how much weight do you have to put on this one to prevent this upward movement? Okay. This computer is saying, James, I made the answer. Okay. The answer is 50,000 garbage trucks, fully loaded. Okay. 50,000. That's equivalent to about 5,000 jumbo jets, fully loaded, is what you need for 1 second's worth of electrons. That's all. It's amazing. I mean, when I knew this number, I was flabbergasted. But it's very simple. Okay, and here's the final one, and I think will maybe impress you. Okay, so you're lying down here, and your wife, girlfriend, whatever, is suspended somehow above you. So it's not exactly too romantic, but okay. We don't have to tell you how this happens, but, and you remove 1% of the electrons, of all the electrons. Of course, she's got electrons and protons. You just remove 1% of the electrons, leaving positive charge. And you do the same for you, leaving positive charge. So the two of you, although you may want to attract, you're actually repelling. And so she's going to levitate. And the question is, in order to prevent that levitation, to keep her exactly in this spot, how much weight would you have to put on her? So I asked for some guesses. A little bit louder, I can't hear.
Another wife.
What?
Another wife.
Another wife. Okay. It's good, but it's not even close.
Several jumbo jets again. Jumbo jet areas again.
Several jumbo jets. Okay, I'll give you the answer.
50,000 garbage trucks.
50,000 garbage trucks. Who takes out the garbage in your family? Okay, well, okay, so I'll give you the answer, but before I give you the answer, I got to tell you that this is not my computation. This comes from the lectures of Feynman that all graduate students in physics read. It's in his book. He gives the answer. The answer is the weight of the Earth. So I presented these to tease you as a kind of introduction to demonstrate how powerful charge forces really are. We dismiss them as trivial. They're overwhelmingly powerful. And wherever you have charges, you have forces, and these forces are much, much higher than any forces that you can imagine. Okay, so we start with that. Charge forces can be astounding, but they're neglected in physics. Well, not exactly neglected, but their magnitude is usually not taken into account. Okay, so the next question is, it's fine that charge forces are pretty big, but can you really have things that sustain net charge? So if you go to your local chemist, the chemist will tell you that everything is neutral, right? You have this glass of water here. There's no way that this can sustain any charge. It's neutral. Is that really true? Because if you can't have charges separated, then it doesn't matter how strong the forces are. So we did some experiments, and Kurt Kuhn was involved with them. We took an electrolyzer, that's the stuff that produces alkaline water, which many people claim is good for your health. It produces water of high pH that you drink, and low pH, which you spit out because it doesn't taste very good. It's good for killing bacteria. So there are two spigots, and you fill one beaker with one of them, another beaker with low pH and the high pH, and then you take a voltmeter and you actually connect these two with a piece of string or something so that current can flow continuously through the voltmeter. So you stick one probe here and one probe here, and you get typically half a volt between these, and that half a volt is sustained over a long period of time. And if you put a resistor between the two, you get current flow between the two. So you've got a potential difference. All this is water sitting here, but water that's so-called high pH, low pH, they're charged. You can sustain charge. Another example is the so-called Kelvin water dropper experiment. This is Lord Kelvin who first did it, and it's really cool. You take some water. This is one source of water, and divide the water into two, and then the water drips into this container and then into this container. And the two containers are made of metal, but you also put a ring here and a ring here, and this ring is electrically connected to this metal container, metal ring, metal container, metal ring. And as the drops fall through here, one of them becomes negatively charged and one is positively charged. And in order to get the electrical discharge that actually happens, you must have at least 10 or 20,000 volts between. So this is one source of water that somehow is able to divide into plus and minus. And we measured very recently, a young student did it, that these charge separations, if you stop the flow before they discharge, they're maintained with a time constant of a few hours, such. They're retained. So you can have a cup of water, a glass of water with net charge, either positive or negative. In fact, if you look visually with a camera at the falling droplet that lands in here, just before these two have reached the point of discharge, so this one, say, has a lot of negative charge, and these droplets are also having negative charge. Here's what happens. So this is the collecting can, and this is the ring that's above it, and we use a laser to illuminate, so you can see that some of them will drop in, but others get deflected and go back up. They're repelling each other, as you might expect, because you have a can full of negative charge, and another negative is coming, so it basically levitates. So basically, this is a demonstration that charge forces can defy gravity. That's how strong these charge forces. So the point is, substances can bear charge. And the charge forces can be huge. So, first question, how powerful are charge forces? I think you got the answer. Second question, okay, where on the Earth do the charges hang out? Most of you have no clue about this. I had no clue until my Russian friend Andrei Klimov worked in my laboratory. Some of you might know him. And just the day he was about to return to Russia, he was telling me about the Earth's electric field. And I said, well, what are you talking about, electric field? You're talking about the magnetic field? No, he said, electric field. I said, I never heard. I studied electrical engineering, and nobody ever told me about an electric field of the Earth. He said, well, something is wrong with your educational system, because every middle school student in Moscow knew, when his roughly contemporary age, knew that the Earth has an electric field, and it's about 100 volts per meter, and it runs normal to the surface of the Earth. So it means that, well, there's got to be a negative charge here and positive charge somewhere there in order to give you that electric field. This really puzzled me until next day I found out one of my students gave me a copy of Feynman's lectures, and there it was, volume 2, chapter 9. Yeah, you know about it, the Earth's electric field. So where does this arise? I mean, we're as Feynman says, a 2-meter person, my nose is 200 volts positive compared to my toes. You know, you never really think of that, but that's the way it is. So I mean, essentially, the Earth really looks like this, with negativity beneath the surface. And some of you, I know, are familiar with earthing, right? You connect yourself, you take off your shoes, and you walk on the beach outside, and you feel good. And you can do this by sticking a rod in the ground and connecting it to your feet or something, and you feel good. And there's a lot of evidence for this, and it seems to be that the reason for that is you're sucking up the negative charge from the Earth into your body, and you need that negative charge, and that's the basis for understanding of how that works. And that's why, of course, in Japan, where people engage in mud baths and other places, it's good for your health because you're basically drawing up the negative charge of the Earth. So where does the negative charge of the Earth come from? Right? Was it born that way? Well, the prevailing theory is it comes from lightning. So the idea is this, that there are many lightning discharges. We don't see too many here, but all over the world, if you integrate over the full surface of the Earth, there are huge numbers per second of lightning flashes, and the idea is that these bring electrons to the Earth, and the surface is considered to be a conductor. So any of these electrons that hit the Earth will spread very quickly all around the Earth, and there are so many electrons coming that they simply can't dissipate. So that's the going theory about, by a going theory, I'm talking about 60 or 70 years ago when Feynman was giving his lectures. At that time, it was the going theory. And I don't know that people have addressed this since then. People have forgotten. It's just like people have forgotten the centrality of water for life. They've forgotten that the Earth has negative charge. It's missed. Now, there's another possibility. The Earth is full of water, right? And it's not just the oceans and the lakes and the rivers and the Black Sea, but it's also all of the vegetation that exists over. And the EZ water, of which there's plenty in the water that's around, and plenty in plants and animals, is there, and that bears negative charge, and the sun's energy builds the EZ, so you have a situation where it's possible that the reason for the negative charge around the Earth is actually the water that exists here and the EZ that exists practically everywhere, and the sun is building that. And so these electrons disperse around the Earth. And that's an alternative explanation for the Earth's negative charge, I think is at least as likely, if not more likely. But we know it's negatively charged, and you need to account somehow for the negative charge. So what about the corresponding positive charges? Where are they? Well, there are many protons evaporate into the air. Remember, you have a situation like this where when you have EZ water, which is negatively charged, and positively charged protons, and it's well known that the atmosphere is full of positive charge. So this is not, atmospheric scientists understand that. So in effect, you have a situation where you've got negative charge here, and you've got positive charge out here in the atmosphere. So once you come to this realization, then you don't have to be a rocket scientist to remember that positive and negative attract one another, well, pretty strongly. So when you think about the Earth and the atmosphere here, and the Earth is negative and the atmosphere is positive, well, the atmosphere ought to stick to the Earth. You know, it ought to stick tightly to the Earth, which it does. Plus clings to minus, and the atmosphere clings to the Earth. And the question arises, does that explain so-called atmospheric pressure? So, atmospheric pressure, what does that mean? You know, we think the atmosphere is pressing on the Earth. And I got to tell you, I've always had a hard time understanding how this happens, how the going theory is. There are a few odd features about the accepted mechanism. It is paradoxical because, you know, the pressure is supposed to arise from the weight of the air molecules. So you got an air molecule down there, another one. It's like a stack of bricks, and they're all pressing down, and that's why there's pressure on the Earth. But it's kind of strange because the air is a gas, and gas is defined as molecules that rarely interact with one another. And so how can they press if they rarely interact with one another? Well, the physicists have come up with sort of rationale that takes a few steps, but you know, another possibility is that if the atmosphere is positive, the Earth is negative, they just stick. And another paradox arising from the standard view is, well, you know, the air molecules are kind of loosely, they hardly ever interact with each other, and there are big winds up there, and so the question is, how come the atmosphere doesn't blow away? See, but if there's stickiness from positive and negative, then that problem is less serious. So here's another paradox that arises from this standard view. It may be another one that you haven't thought of. The atmosphere is not just oxygen and nitrogen. It also consists of trace gases, but they're not quite so trace. So argon, for example, is about the atmosphere is about 1% argon, and of course there's CO2. And those are denser than oxygen and nitrogen. So a question arises with these gases, you know, after a few billion years or so, even though there's wind that's mixing, but there should be a tendency for the heavier ones to settle at the bottom. And if that's true, then the question is, well, you know, we might have a problem here. So that's a paradox that arises from the point of view of considering the weight and density of the molecules that are sitting there. It's kind of simpler to think that the positive sticks to the negative, and so effectively the atmosphere is glued to the Earth. And imagine if that were not the case. You know, just think about it. So the Earth is spinning, and the surface velocity is very high. It's like the speed, twice the speed of a jet plane. You have the atmosphere over here that's not stuck to it, it's just there. So the Earth's surface is spinning around at this huge velocity. And effectively, if you're standing on it, you'd expect a wind that's blowing at 1,500 kilometers per hour or something like that all the time. But if there's stickiness that's here, they cling. That doesn't happen. So we don't have to worry about the wind. So the suggestion of this is that atmospheric pressure might arise from the positive charges pressing on the negative Earth. Okay, so I've explained where I believe the charges on the Earth hang out. Okay, the next question, are there substantial charge gradients that occur? Okay, the first point is this. Okay, if you look at, here's the Earth, and here's the atmosphere, and we know that we have positive charges here. Now here's a test charge, just a charge that you use to see what's going on. You can move it around anywhere you like. And if you put it right here, then you'll be in the vicinity of a lot of positive charge, and it will look like it's pretty high. If you raise this higher, the charges are less dense over there, and it should be actually lower. So the proton concentration, or the field strength, both decrease with increasing altitude. So the field might be 100 volts per meter here, but as you go up higher, it diminishes. Okay. The next point is that so the field strength diminishes with increasing altitude. Now here's the important one, and more important, is that the field strength increases with sunshine. So why is that? Well, this is nighttime. There's not much evaporation at nighttime because there's no sunlight, and so all the charges then are pretty much, or should be, I'll show you the evidence, should be kind of down here. Now during the daytime, the same test charge sitting here should feel more positive charges, because now the positive charges are extending way up into the atmosphere. So there's a big difference between daytime and nighttime, and that's the critical point. And so the electric field varies with the time of day. If you're sitting here somehow, you're going to experience a high electric field, and if you're sitting here, a lower electric field. And the evidence for that has been in existence for a long time. The evidence looks like it's from here. So this is the time, GMT, from 0 to 24 hours. And this is the electric field. Let's take, and this is done for 3 different regions around the Earth. So obviously it's not pinpointed with high spatial resolution, but take Africa and Europe over here. So at Greenwich Mean Time, 12 o'clock right here. And so at early afternoon, the field is the highest. And then it drops down, it becomes lower and lower, and then it rises up again. So it's cyclic, it occurs every 24 hours. And the same thing happens in here, the Americas. This happens later, and Asia and Australia and such as earlier. But look at the difference in magnitude. For example, look at the Americas, and you can see that the field strength, this is measured up high in a balloon, right? It's, the value here is like 10 or 5 or 8 or something like that, and it goes up to about 75. It's 10 times. The difference between day and night in the electric field is 10 times. It means up there, the amount of positive charge that exists up there varies by a factor of 10 from day to night. This is not 10%, but this is a factor of 10. It's astonishingly large. So, when you're at the boundary, if you're sitting here, or if you're sitting here, the boundary between day and night, there's going to be a gradient. You're going to have more positive charge in the atmosphere here and less here. And of course, the same thing on the other side. There's a day-night boundary and a night-day boundary. So, do substantial charge gradients exist? Yes. Lateral charge gradients exist of appreciable magnitude. And remember the force that we're talking about of these charges. I tried to demonstrate to you how big they are. So, next question. Can charge gradients, those charge gradients I'm talking about, drive the prevailing winds? So we have something like this. You have, remember, the region that's already illuminated has lots of positive charges up here. Here's New York and here's Seattle, right? And it's nighttime in Seattle, and the sun has already risen in New York, and gradually, a little bit later, it's going to rise here. But meanwhile, you have positive charges here and very few positive charges here. So the positive charges are going to want to move. They want to move away from the other positive charges into regions with fewer positive charges. Those positive charges moving, dragging the air molecules with them, create wind. And I think that's the origin of wind. So we have a morning boundary and an evening boundary. And what can we learn from that? Okay, so here's the morning boundary. So remember, the sun is beginning to rise here, and this is going to be progressing in this direction. So you have some positive charges, not a whole lot, because there hasn't been a whole lot of time of exposure from the sun. So the positive charges are beginning to accumulate and rise up, but very few here. So you should get a wind, but the magnitude of that wind is not going to be that large. Now, so let's look. This is I'm sorry, this diagram is a bit hard to understand, but this is this is different positions along the Earth. So let's say in this position here it's dark. This is nighttime, and here it's light, and here it's light as well. And so here is the morning boundary. It's just what I showed you. So you have positive charges beginning to build up, and very few positive charges here. And so you're going to get wind that goes from east to west. Of course, once it starts blowing, it has to blow all around the Earth because it's continuous. And those winds are called the trade winds. Those winds from east to west, low-level winds, not too high in magnitude. That's how Columbus got to the New World, and how sailors take advantage of the east, the wind blowing from the east. On the other side, the boundary between the, say the evening boundary, where it's the afternoon, charges have built way up there, a factor of 10, remember, and this is dark, and so the gradient here is much larger because you have a huge number of positive charges way up, and of course you get wind, and that wind, I believe, is the jet stream. So you know the jet stream because if you fly from Seattle to Varna, it takes less time to go in that direction than in the other direction. The difference is about 20%. These are very substantial winds that blow reliably up high, and I believe that this provides a possible explanation for that. So these are weak trade winds, and these are strong jet stream winds. So can charge gradients drive the prevailing winds? I think the answer is yes. Now, then, the obvious question is, well, can those prevailing winds spin the Earth? And the idea is something like this. It's not very complicated, that if you've got winds up there and the winds are blowing and the Earth is here, they're going to drag the Earth with it. In fact, it's difficult to imagine how this could not happen if the wind is steadily blowing in one direction all around the Earth. So the advantages, you might say, of this wind mechanism, the first is that, you know, we all think, if we think of the spinning of the Earth at all, we presume that the Earth has so much inertia that it just keeps going, and how it got started in the first place, we don't know, but this is the assumption. But there's a problem, there's a problem in that people have measured the velocity of spinning of the Earth. If it's inertia that keeps it going for billions of years, there should be no variation. However, there are hour-to-hour variations in the speed, which means it can't be inertia. There has to be some energy, some force, some energy that keeps it going round and round. Just the same as when the Earth revolves around the sun. There has to be an energy that moves it in the tangential direction. I'm not going to speak about that, but this has to be understood, and right now it's not understood. So that's an advantage, is that we have energy that's driving it. It's the sun. It doesn't depend on the inertia. The sun's energy is the ultimate driver. And as I said, it explains the known fluctuations in rotation speed. So can the prevailing winds spin the Earth? And we discussed, and I think the answer is yes. And finally, as a coda, I would like for you to think about the flow of charge that we're talking about, the wind, and magnetic fields. Okay, so I've suggested to you that there are charges that run round and round the Earth, especially the jet stream, full of positive charges that keep encircling the Earth and keep flowing. That's current. Some of you realize that when you have current flow, as in current in a wire, you get a magnetic field around it. And so what we're talking about, if you have current that runs in this direction, my education in electrical engineering comes in handy sometimes, it's the right-hand rule that shows you the direction of the magnetic field. Okay, now please consider what we've been talking about. Here's the Earth, And here are the jet stream winds high up that are running all around the Earth in the direction that's shown. If you take the right-hand rule, it means that you've got a magnetic field that runs like this, around and around the Earth. So there's one element of this that's high up, maybe the so-called Van Allen belt, and there's another that's close to the surface of the Earth. This could conceivably be the origin of the Earth's magnetic field. We think of the Earth's magnetic field as arising from inside the Earth, but nobody's ever been there to check it out. It's possible that the Earth's magnetic field may arise externally and not internally. So the conclusions are that charges, first of all, can exert forces that are beyond our imagination. I presented 4 examples to you, and I think for most of us it's just almost inconceivable that they're that large. But if we take Feynman and such as reasonable sources, then we have to admit that these charge forces are huge. And the Earth itself, unlike what I was taught as an electrical engineering student, where you plug it into ground and it's zero, but it's not zero, it's negative. Real surprise. And the atmosphere is positive, and the two cling to one another. The attraction could create what we call atmospheric pressure. And the sun's energy builds that atmospheric positivity through evaporation. There is another source too, but I won't go into that now. And the nighttime regions have less atmospheric positivity because there's less evaporation. And I think the charge gradients that come out of this analysis could easily drive the winds that we experience. You feel a gust of wind, and we don't even think about where that gust of wind can come from. We may think it's pressure gradients, but where do you get pressure gradients? And the winds create drag, which may drag the Earth and drive the Earth's spin. And finally, the Earth's magnetic field, this lateral flow of current could create the Earth's magnetic field. So electric forces may govern the universe, and water charges play a central role in all of this. And I guess a more general point is that sometimes alternative theories can make sense, and I want to show you in the last slide an example of this. We're going to be Tom Weissmuller will be talking about weather and the rise of the oceans. There's an alternative view that's not only different from the worldview, but also different from Tom's. And the rise of the ocean's waters could have a different origin. Sorry. We have a problem in the U.S. Okay, so what makes the world go round? I think the answer may be water and charge. Now, okay, and finally, I want to show just a few slides about alternative ideas. Last year, those of you who were here, I talked about the Institute for Venture Science, and this is another endeavor in which we're engaged. And this is an institute or a foundation that we're building. It's going to be an international foundation to foster promising ideas that challenge conventional thinking, just like the alternative theory for the rise in the sea. A week ago, less than a week ago, we decided to have a launch symposium, and it took place in Seattle. And several people were there, including Luc Montagnier, and we put together the event, and many people came away feeling inspired. That was the comment, and it actually started with an evening reception at our home, which was nicely catered, and it didn't rain, although we had actually a tent. You could see Lake Washington behind. We have a nice view. And of course, the host and hostess were there too, and a good time was had by everybody. And then the next day, so this is sort of to loosen up the crowd, and the crowd consisting mostly of people of some means who want to do something about changing the world. And then the symposium took place on the University of Washington campus, and you can see that there even were some questions. And it started actually with Barry Marshall, and I think probably most of you don't know his name, but Barry Marshall won the Nobel Prize for discovering that ulcers could be caused by bacteria. And he had a devil of a fight against the establishment who said there's no way that bacteria could survive in the acid environment of the stomach. And finally, he couldn't convince anybody that this was real. And so what he did was to swallow the bacteria, and he got an ulcer and took some antibiotics and cured the ulcer. And then they gave him a Nobel Prize. And of course, Luke was there presenting a beautiful presentation. And I think these and two other speakers dazzled the audience and underline the need for this kind of organization, because it's really difficult for ideas that challenge, many of you know that challenge the status quo, really difficult for them to gain any traction. And so the idea is that this institute will not only fund, for example, a round earth idea in a flat earth environment, but if we receive an application where it's suggested that the earth is round and everybody believes it's flat, if we fund that one person, I think this is a really important observation, probably that person will get nowhere, because all the flat earth people are going to say, oh, he's a crackpot, don't even pay any attention. So in order to circumvent that, our idea is if we get one round earth proposal, we think it's a good idea, not only will we fund that person, but we're going to look for a dozen other people independently around the world who share that kind of vision. And then next year, at the annual meeting of the Shape of the Earth Society, you have a dozen people reporting that the Earth is round, and that can't be ignored. And so we expect revolutions to happen rather quickly, in contrast to today's science, where revolutions are rare. Is that you have a revolution, scientific revolution, which gives you fresh insights and new solutions to all the problems that plague the world. Many people feel that we're in imminent world meltdown, and something needs to be done desperately to change that. And so it leads to a future. But it's not only the new ideas that bring a brighter future, but in reality, every time you have a revolution, a scientific revolution of some sort, new technologies emerge that you never would have dreamed of. For example, in the semiconductor field, the idea that you can dope some semiconductors, 60 years ago at Bell Labs, all of the technology that's before us right now, iPhones and whatever, arose from that simple finding. And so the new technologies will bring economic revitalization and a brighter future. And so this is the aim of the Institute for Venture Science. Unthinkable ideas today to receive wisdom tomorrow, growing fresh branches on the tree of knowledge. So I think I will end there, and if any of you know some people of means who are open-minded and want to do something with their money, please don't hesitate to connect us. I think I will end here, and thank you very much.
Well, thank you very much for your inspiring talk. We know now how the world goes round, but also you're going to make the world, all around the world, financially.
Well, we hope so.
Anybody has some finances? Questions?
Hi, very interesting talk, that I find that interesting, but I was just wondering if there are any other planets that you think this applies to, ones that, there's many planets that have very different atmospheres to ours, obviously.
Yeah.
So do you think it applies to all of those, everything's spinning, so?
Yeah, well, I myself had that question early on. I said, well, gee, all the planets revolve or rotate on their own axes, and I thought, well, if this has something to do with the atmosphere and charge gradients, I'm wondering whether those other planets also have atmosphere. So I started looking and researching. Well, it turns out that they do. And it is not so widely known, but if you look and investigate and look at the papers that have been produced on these planets, we know, for example, Venus is full of atmosphere, but actually all the other planets, every single one of them has an atmosphere. So if what I presented to you has some merit, then it does explain why all those other planets rotate as well. By contrast, if you look at our moon, there's no atmosphere. The moon doesn't rotate. And so again, there's a correlation between having an atmosphere and rotating. You know, if you look at the moon, you always see the same side of the moon, right? And the moon is going around the Earth, but since we always see the same side, it means it can't be spinning, and it's not spinning. So.
Thank you.
There is also parameters we forget about is the exchange of the mass of the Earth with time. Is that mass constant from the beginning or not? And a physicist told me that this could change in mass be due to the rain of neutrinos particles going to the Earth all the time without being discarded by fields of any kind. So he could explain earthquakes not by the change in the plaques, movement of plaques, but the fact the crust of the Earth will break down.
Yeah, I mean,
mass increase.
I think that could well be. I mean, along the similar lines, my thought about that is that the Earth is receiving charge all the time. It depends on the sun, you see, and if the charge increases, is quite almost along the lines you're talking about. That could create fracture, or enough force, enough repulsive force that will unleash the earthquake. You mentioned neutrinos, and I guess it brings me to it's slightly different topic, and I apologize, but you know, I think there's a problem with our understanding of the structure of the atom, because it has to do with charges also, and it has to do our understanding of the atom. We have neutrinos and we have 60 other subatomic particles. It would seem that, you know, a theory that's adequate, we wouldn't have to add a new particle every 2 or 3 years. And this is, I find this rather disturbing. And so, you know, if you go back to starting with Niels Bohr and the structure of the atom, there are a few problems with that are so simple. So I talked about the power of charges. So you have in the nucleus, in the Bohr model, you have a lot of protons that are stuck together. They exert an enormous repulsive force. So you'd expect that the nucleus should blow up. It should explode. But of course it doesn't explode, and the physicists recognized this fundamental problem. So they invented the strong force. And nobody has ever independently identified a strong force. It's like a bandage that's put around the nucleus to keep it from blowing up. And then, you know, another problem is you've got a positive nucleus, and then you've got negative electrons. Well, it seems to me, I learned in basic school that negative and positive attract. So how come the whole atom doesn't collapse into nothing? Yeah, well, you could call it spin, but still, despite the spin, where does the energy for the spin come from? Who's giving it energy? And despite the spin, you still have the attractive force, and so the whole thing should collapse. So it's possible that our fundamental understanding, even as fundamental as the structure of the atom, may be completely wrong. Yeah, absolutely. Yeah. It's exactly true. So Luke is saying, without a microphone, you know, that planets are also revolving around, and so you know, an issue is what keeps it going around. Why we have gravitation that should keep it, that should pull the two together, but it keeps going, and the planets don't collapse into the sun. You need a force to keep it going. Where does that force come from?
Zero-point energy.
Well, okay, what's zero-point energy? How do you define that? How do you explain it? It's a vague concept. There's some energy out there, but what is it? And who? Yeah, I've heard that too.
It's not vague, it's simply out of education.
Oh, out of education. Yeah, it could be. Yeah,
You see,
sure.
if Copernicus is not in the university, then Earth is flat.
Yeah, right. Well, it is flat. You can see out there.
Oh, exactly.
It's flat, right?
Okay.
Sorry. Yeah.
Jerry, I love the way you think. A couple of refinements, though. In the classical atmospheric science, you got the tropical easterlies that come east to west, and the westerlies go west to east. And there's somewhat of a net computation there in terms of the net speed of the Earth, but there's a variability they call that gives rise to the Chandler wobble in the minute fractional changes in the orbital dynamic of the Earth. They adjust second, fractions of a second per year or per decade and so on. There's another very interesting thing is at the highest altitudes, there's a newer discovery on upper stratospheric winds that blow very, very fast, and they're considered to be downward advecting their momentum to drive the winds closer to the surface of the Earth.
Oh, I didn't know.
This would bring into play cosmic forces beyond the Earth itself, such as things within the plane of the solar system, within galactic streaming, other kinds of things that I use in my own work, but it just expands it a little bit further.
Well, Jim, I'm right with you. I didn't mention that, but I think that those cosmic forces are really important. I just didn't want to complicate things, but you know, you have positive charges coming in, alpha particles and protons that we get from all the stars. We get it from our star as well, from the sun. So you've got positive charges coming from the Earth, and we call that solar wind. But that also adds positive charge to the atmosphere, see, and that positive charge complements the positive charge that I was talking about. So a good part of it may indeed come from cosmic sources, from our own sun, and also from outside. I agree with you.
So my question is if I'm over here.
Where is here? Oh, okay.
So
Thanks.
if it's 10 to the 38th more powerful than gravity, how is it so overlooked? I mean, when you talk to people about electricity or charge having such an important role and being so powerful, but it's been overlooked.
That's a good question.
What would they
I
say?
think,
What would the status quo say to charge having such an important role, and why they overlook it?
I think that people have not gone through the type of logical analysis to say, well, what if? What if we have these charges? What would be the consequence? So atmospheric scientists, for example, they know about the positive charge, and geophysicists know about the negative charge of the Earth. These are common, but somehow the two disciplines don't meet, and the people who are studying the rotation of the Earth, there are not too many. They're distinct castles that have risen in science with big barriers, big moats around them, and they don't actually come together to do that. And also, there's a kind of inertia in science when people, if you have your own idea about a particular phenomenon, and you've built your career on it, and someone comes and says, well, you're wrong. We're humans, and we have a tendency to want to stick to the ideas that are familiar and comfortable to us. And so the idea of charge, I think that few people have actually brought this to the attention. You can easily do the calculation. Any freshman physics student can do it. But to go from the calculation about the strength of the force to say, okay, we know it's big, then what if? Challenges many domains of science. And so people don't like to go in that direction. That's one possible explanation. But you can do the calculation yourself. It's really simple, and find out that these charge forces are absolutely enormous. And okay, I won't go on and on because there are more questions.
Hello. I have been doing some calculations, and I want to know, in some of these cases, how much you've gone through and done the maths of the conventional theories and show that they come up short. Because, to use one example, you talked about the atmosphere should be spinning off into space, and well, the equator moves at about 500 meters per second. The average speed of an oxygen molecule at 25 degrees is, again, about 500 meters per second. So there are things moving very fast. But the escape velocity of the Earth that you need to get out of the Earth's gravitational fields is 11,000 meters per second. The atmosphere isn't moving fast enough to escape. So Why do you think that it would? Why isn't gravity sufficient for you?
Why isn't gravity sufficient for me? I'm not sure. See, I think gravity is the charge. Nobody understands gravitation. Let me just
We
ask
understand gravitation enough to know that it doesn't work. It wouldn't be sufficient for it to be the charge, because the charge obeys a 1/r squared force. We know this and we measured it, and we used to think that's how gravity worked as well.
Yep.
That was Newtonian theory. Then we noticed that the precession of Mercury isn't right in that. So and Einstein came up with general relativity and showed that that predicts the precession of Mercury correctly. So how could charges give rise to the shape of gravity that we see in general relativity?
Well, I think you need to go back a step and ask the question in a different way. If there's charge, I think there's no question about there's charge, what would be the effect of the charge? And the effect of the charge, if you have negative charge beneath the surface or from the surface down, will induce positive charge by Faraday's law on anything that's above. So you're standing there, and the negative charge of the Earth will induce positive charge on the bottoms of your feet. That will pull you to the Earth. It's very simple, and it doesn't depend on any relativistic or other considerations.
Really quick one. Sorry, me again. You've given a great talk on what makes the Earth go round. What makes it wobble? Have you given any thought to precession?
No, I haven't. However, if you remember that graph that I showed about the GMT 24 hours and the electric field, and I showed, or it was shown that there's a factor of 10 difference. The top curve, which I didn't talk about, integrates it all around, and at a certain time during the day, there's a maximum, and it's possible that that maximum is responsible for the wobble that you're talking about. I'm not sure, it's just one idea.
I think we have to stop for the next presentation, but we can ask Professor Pollack all the time.